Still using your monkey eyeballs to measure acidity? That's no way to do quality control in the 21st century. In my last video, I showed how you can use a pH probe to measure dilute solutions of vinegar when pH papers just aren't precise enough, which will be critical in my quest to make aspirin. As with all precision instruments, there's a trade-off between precision and noise. This video will show you some techniques I use to get the full potential from this powerful tool. Using one is very simple. Rinse your bulb with neutral water and pat dry after each new sample. Then, submerge in the sample for 2 minutes to allow the readings to steady out. Even after you do this, you'll notice the readings jumping around a little. Which number do you write down? One way to get around this problem is to interpret the jumpiness as random noise. So, take the last 10 to 14 seconds worth of measurements after it steadies out. You'll get a cluster of data whose shape we'll assume to be due to some unknown process, and we'll interpret the mean of the samples we collect to be the true pH value. Now, we could just calculate the mean from this data and call it a day, but the problem is that that would just be the mean for the data we have. If we kept sampling, our answer would probably change, and worse yet, we'd have no idea how much more data we'd need to collect for a good answer. What we really want is a way to calculate the mean from all past and future data. That is, the underlying mean of all the measurements we could possibly collect. Is such a thing possible? Yes, and all we need is the data we already have. The first thing we do if we want to predict what the future data will be is to figure out what the process is that causes the data to cluster in this specific shape. And actually, we don't need to figure it out. We can just use this data to tell us how to construct another data set with the same underlying mean, but whose jumpiness we know will fall within a predictable shape, like a bell curve. Then we can just work with the bell curve shape to find the underlying mean. So, is there a way to use this data to create such a cluster? Yes, we form 20 subsets of 3 data points each, randomly chosen from the data we collected, and calculate the means of these subsets. According to the Central Limit Theorem, the means of subsets from any cluster shape will form a bell curve, and that bell curve will have the same underlying mean as our raw data. This theorem is just what we need. Now, you could calculate this by hand, but I prefer writing a program in Octave to do it for me. You can see that this data really does have a bell curve shape. To find the exact shape of the bell curve, we need the underlying average distance between the points we have now and the middle, and any points we might get in the future. Again, we don't have data from the future, so we just use the average distance between the points we've already collected. That smushes out the bell curve into another shape called a t-distribution curve. Now that we know all future measurements will fall in this t-distribution curve, producing a range for the mean underlying all of this is as simple as finding a boundary that covers up a certain percentage of the curve, starting from the middle. You want a range where 50% of samples will contain the true pH value? Just cover up half the t-distribution curve. I use the range that will contain the true pH value 95% of the time, and in research where people use statistics, it's basically a meme that 95% is good enough. So that's how you use a pH probe, and really any measuring method that suffers from noise.